Okay, D, so I'm going to change the cos to theta. So what formula would you use? What formula do you want me to use? You've got 3 versions of cos to theta, right? Which one am I going to use? Am I going to use cos squared minus sine squared? 1 minus 2 sine squared, or 2 cos squared? The third one, right? Because I want to leave everything in coses. So I'm going to replace this with 2 cos squared theta minus 1, okay? Then I have a minus cos theta. So it actually looks a little more complicated now. However, it's not more complicated because I have cos theta, and I have single angles, right? So now what do I do? How do I proceed from here? Yeah, so just put it in proper order. This is a regular quadratic then, right? So let's hope this one factors. So I'll have a 2 cos theta and a cos theta. My last terms can only be 1s. I need a -2 and a +1 here then, right? Or a -1 + 1. Okay, so I have cos theta equals -1 or cos theta equals 1. These are both exact values, special angles. I'm answering in radians. Cos equals -1 at pi. Oh, thank you. Sorry. Ugh. I forgot my 2, right? Thanks, guys. 2 cos theta equals -1. Cos theta equals -1/2. Okay, so that happens at my pi on 6s. In 2 and 3, or sorry, my pi on 3s, sorry. So that will be what? 2 pi on 3 and 4 pi on 3. And cos equals 1 at 0. Okay, 2 pi is not included, you can see, so it's just 0. So these would be my answers. 2 pi on 4, 2 pi on 3, 4 pi on 3, and 0. Okay. With this one, I think you're going to do something similar to what we talked about at the beginning of class. You're going to use an identity to switch out what? What are you going to switch out here? I've got a cos squared and a sine theta. You're going to switch the cos squared out to 1 minus sine squared. Here, I have cosecant squared and cosecant. I think I could factor this one. And at the very end, you would just switch to sines. So that's it. And then you had another one in number 7. You had a tan squared and a tan, a sine squared and a sine. You should be able to do that. I left out number 8. We're going to talk a little more about number 8 today. So if you got here a little late, remember your test is on Friday. It's on identities, applications, and equations. I'm going to finish up a few equations today. You're going to kind of be able to do this type of equation. We're going to talk about a few more equations that involve these double angles too. Okay. So if you get anything tricky at all, like so far we had a 2 theta and we had a cos squared and a sine mixed up, your first thought should be use identities, right? Use identities to get everything in terms of one trig function and just all single angles, right? So where did we leave? Were there any other questions on anyone who came a bit later on any past homework? No? Okay, so I am going to back it up, I think, to, you know what, I think I'm gonna work forwards again and then backwards. What did I do here? I lost my, sorry. Okay, let's go back to page 15. We're going to finish up all your examples. It kind of ties into what I want to do. So using double angles. So we've got double angles to solve identities. This is a bit of a repeat. So I have cos 2x equals 1 minus 2 sine x. So what am I going to replace here? Cos 2x, right? So I would, and the reason is because I have mixed terms, right? Not like terms. So replace cos 2x with an identity. Is that what occurred to everyone first? Okay, so go ahead, proceed and solve that one, please. If you're done, I want you to finish up and try B on your own too. So I'm kind of challenging you here. Page 15. We left a few of these out, so we had to move backwards.
Since you have a sign x here already, I'll probably replace it with the signs, because then you're everything in terms of sign, right?
Okay, so it looks like everyone's tried the first one, right? So I have cos 2x, so I replaced the cos x with an identity. What did you, which identity did you use for cos 2x? The 1 minus 2 sine squared, right? 1 minus 2 sine squared. What was the reasoning for doing that, D? Why did you change the cos 2x to the 1 minus 2 sine squared?
Because we want to put the same sign.
Yeah, you want to use the same trig function, right? The right-hand side has sines, you want the left-hand side to have sines. So now I have a quadratic, right? I'm going to move everything to the same side. So I'll have minus 2 sine squared x, 1 minus 2 sine squared x, plus 2 sine x, minus 1 equals 0. The 1's cancel. I'm left with negative 2 sine squared x plus 2 sine x. I think I'll divide through by negative 1 just to make my first term positive. So that'll become a minus. 0 divided by anything stays 0. Okay, can I factor this? Yep, GCF is 2 sine. And I want to factor, because factoring, and if I've got a quadratic equal to 0, as soon as I put it in factored form, then I can use my zero product rule, right? Either this equals 0 or this equals 0. Okay, my domain is in radians, just one rotation. So divide by 2, I'll have sine x equals 0 again. That happens at 0 and pi. Notice 2 pi is not included in my search area, so I just have to leave it 0 and pi. And here, sine x equals 1, and that happens at pi on 2. So these are my solutions to this question. Okay, good? All right, let's do this one. Half sine 2x minus cos squared x equals 0. Problem? What's the problem again? Different trig equations, right? And I have too many other numbers attached. I can't just divide them, like, and I have a cos squared. I can't divide out by a cos like we did before to create a tan, right? It just doesn't work. I have too many other complications. I have a double. Okay, so I'm going to have to replace my sine 2x. Agreed? I think. Even though I have cos squared, the reason I'm going for the sine 2x is because it's a double angle, right? This is at least a single angle. And I can't do anything with double angles either. So I'm going to replace that one. You might have done something different. Did anyone else replace this? And then you got 1 minus sine squared, right? You'd still have to replace this, I think, though. Because you have the double angle. Yeah. So I would replace this with 2 sine x cos x. I find the double angles harder to work with, so that's what I tried to replace. And see what happens in the end. So then I have a cos squared x equals 0. Because I've got my single angles then, at least. Okay, so these guys just cancel each other out. So as John said, I'm left with sine x cos x minus cos squared equals 0. So again, I would always attack the double angle first. Now, I can factor again, right? I've got a cos. So that leaves me with sine minus cos equals 0. Okay, this is a bit tricky. Okay, so I've got my zero multiplication rule, right? Think about this for a sec. I've got it all factored for you. You just have to come up with the two answers. Again, the domain is 0 to, it's the same domain as before, so it's 0 less than equal x less than 2 pi. So I've got it factored. Use the zero product rule and tell me what the answers are. I'm going to give you a few minutes. Okay, so what's the first answer, I suppose? What'd you do first? Anyone? Where'd you go from here? Cos x equals 0? Okay, when does that happen? Perfect. Thanks, Ibby. I heard you loudest. Okay, what's the next thing then? The next thing means sine x minus cos x equals 0. We actually did see this before in class. I don't know if you were here that day. So there's two ways you could approach this one, right? Curious, anyone want to shout out what they did? Move close to the other side, okay? So okay? Yeah. Now, did anyone solve it just leaving it like this? You did it that way, John? So you said, okay, where does sine exactly equal cos? That happens at pi on 4 and 5 pi on 4. Now you could have done it, again, you could have done it a different way, right, Joanna? You could have divided by, you could have stopped here, you got your sine x equals cos x, or you could have done it even before you moved it over, right? Then what did you divide by? Sine x?
Yeah.
Did you, Joanna, or cos? Cos x, okay, so I'll do Joanna's.
They're the same.
It'll still work, right, either way? So tan x, where does tan x equal 1? Pi on 4, but pi on 4, right? Did you divide by sine, maybe?
Yes.
Okay, sine x equals cos x. The more ways you have to do something, the better, right? Because when you're in a kind of a stress environment, like a test, if you've got 3 or 4 different strategies to fall back on, you'll never be stuck. So then you said 1 equals cotan. Where does cotan equal 1? Pi on 4, 5 pi on 4, right? So great. If you guys remember that, that's awesome. So we have 4 answers. 2 here, 2 here. Okay, now we're kind of doing the same type of thing. Actually, let's flip. I know I'm all over the place because it's a little out of order, but that's okay. I want everyone to flip to the last page of this book. Now, there were a few of you that asked me about this one, right? I know Rahel was looking at it. John, I think you were as well, right? Did anyone else look at this one? Like, I didn't assign this one, but people flipped the page. Because on Friday, we worked through quite a few of these, and then we flipped the page. Okay. So, did you come up with an answer, Rahel? You did? No. John, did you come up with an answer? No. What was the problem here? Sorry. I think the only thing you can replace sine 2x with, first of all, there's only one trig function, right? The only thing you can replace sine 2x with is what? That's the problem, right? So you could only replace it with 2 sine x cos x equals 1. So we get rid of the double angle, but we get 2 single angles. The problem is we've introduced cos into the problem. So now we have what? 4 sine x cos x equals 1. We can get as far as sine x cos x equals a quarter. And then we're stuck, right? Because we don't have that zero property rule anymore. So we need another strategy for these ultra hard types of equations. Okay? And that's what I'm going to introduce to you today at the beginning of today's, or sort of towards the end of the class. So we need another strategy. We can't use identities. Or I guess I should say identities won't help us. With this equation. So if you have, with this multiple angle, now multiple angle is what I call this, right? This is the double angle, it's a double angle. Normally, I can get myself out of trouble by using a double angle identity, but there's going to be some cases that I just can't get myself out of trouble, so I have to use a different technique. So this is what the technique we're going to use. Now, the search area, I'm going to say the domain was 0 less than equal x less than 2 pi, okay? So it's the same domain we've been using. That means I'm going to just search, nothing fancy, it's just one rotation. So how I have to solve these guys is, I was asked to solve for double angle. That sort of changes your domain at the beginning. So what happens is, I have to think of this for a double angle, 2x, the domain changes to, okay, so see if this makes sense to you. Instead of 0 less than equal x less than equal 2 pi, I have a 2x here, right? So my whole domain has to double. 2 times 0 remains 0, so my starting position is the same. I doubled the x, so I have to double the 2 pi and I get 4 pi. Okay? Because what does that 2x mean in graphing terms? Let's just stop. Let's just say let's say I wanted to solve this graphically. Y equals 2 sine 2x minus 1. Sorry, I don't know if you guys can see that. Okay? Because I can always solve things algebraically or graphically. What does that 2 do to a graph? What is that value, by the way? That's b, right? b equals 2. So that's the frequency. That means there's two complete cycles of the graph in a distance of 2 pi. Or what would the period be? Pi, right? So what that means, and we're just going to go over here for a sec. So if I had this graph and what the d is -1, there's no shifting. It's a very large, or it's been elongated, right? So it has a distance, it would go up to 1 and down to -3. Okay, so my graph would look like this. Okay, sine starts on the median. It finishes one cycle, and then it finishes a second cycle, correct? And this is my median. That's what b equals 2 means, and that means this is 2 pi because it completes one full period pi. Agreed? So that changes what I'm saying to you is it completes 2 rotations in a distance of 2 pi. Okay? That 2 means I have to search 2 rotations. So that means I'm not really searching 4 pi, but I'm going to go twice around the circle. This means we find solutions twice around the circle. 2 revolutions. In essence, that's what that means, right? Now, we're going to see we actually don't search to 4 pi. It's just a technique that we use. So when you see a double angle and you can't use identities, that's what it means. Search the unit circle 2 times round. Okay, so what is she saying by all this? Well, let's take a look. All I can do at this point is just isolate the sign. So I have sine 2x equals 1/2, okay? This is my new theta. Think of this as theta. So I'm just going to say theta equals, well, where does sine theta equals 1/2? Think of sine theta equals 1/2. Okay? So you can think of it this way. Replace 2x with theta, right? Sort of what we're doing. John, where does it equal 1/2? Here and here, right? So pi by 6 and 5 pi on 6. Okay. So theta equals pi on 6 and 5 pi on 6. but I have, that 2 means it completes 2 cycles, so I have to go one more cycle around. This is where we use our coterminal knowledge, right? Okay, let me go all the way around again and get the next coterminal. What would that be? Pi on 6 and another 2 pi, 13/6, right? Okay, and what about this one? 5 pi and another 2 pi, 17 pi on 6. Okay, so, and that's it. Now I've completed 2 rotations, right? So my answers are pi on 6, 5 pi on 6, 13/6, and 17/6. Okay, so these are my set of answers if I was solving for 2x, but you're actually solving for x. Okay, now we solve for x. Okay, use your algebra skills from grade 10. If I had 2x equals a value, if I solve for x, I would divide by 2. So dividing by 2 doubles the bottom, so my final answers are and that's my final set of solutions. Definitely a bit of a strategy, right? But I was forced to use that technique because when you just have one trig function and a multiple angle, there's really no identity that could help you in some of these multiple angles. So we used our knowledge of periods and stuff, and basically we just said, what it boils down to is if you have a 2x here, I'm going to find my set of answers in 2 rotations. What if it was a 3x? I'd have to go 3 times around the unit circle, right? Because my domain would be up to 6 pi, so that's 3 rotations. What if it was half x? What would I be solving for? Everything would be cut in half, right? 0 divided by 2 stays 0. I would be asked to solve for half x, so I'd only be solving up to pi. I'd only use answers in the first 2 quadrants, right? Okay, so there were a couple in your textbook, but there's a couple more in this little book, so I'm going to sort of flip backwards here and find the next 2. How about this one on page 18? Solving trig equations with a multiple angle. Okay, I only did that one first because people were asking me about it. So let's say this one, sine 3 theta equals root 3 on 2. All right, so initially I think, could I use a trig identity? No, not easily, right? I have a 3 theta. We don't have any identities with 3 thetas in them. So in this case, there's nothing I could do with identities. I think I would be forced to use my new technique, right? So if you want, you could substitute 3 theta in for an x, or you could just try and kind of do it like we did before. Okay, so what does that 3 theta do? Well, normally, I'm being told to solve from 0 less than equal theta less than 2 pi, right? Now I'm going to change my search area. 3 theta, 6 pi. So you can either do that to remind you, or you can just look at that 3 and say, okay, I have to go around the unit circle 3 times. So I'm going to let you try and use the techniques we just did to solve for theta.